In this next section, we're looking at electronegativity and bond polarity. So you should really be able to understand electronegativity and use it to determine the polarity of bonds, as well as use electronegativity and formal charge to predict the charge distribution in molecules and polyatomic ions. So remember that electronegativity is the ability of an atom in a molecule to attract electrons to itself. Think electronegativity, electrons are negative and it wants them. It has an electron affinity. It's wanting those electrons. The ionization energy is the measure of how hard an atom holds on to its electrons. So here's our electronegativity sheet here. Again, electronegativity is the tendency of an atom to polarize a bond. Follows the Z chart on the periodic table. And what we can see here is that metals have low values. We know that these guys would rather be give up their electrons, not gained more electrons. So they have low electronegativity over here. The metalloids have intermediate and these nonmetals have high. And we're going to come back to this to show how we would show electronegativity differences. When we are looking at two different elements or atoms involved in a bond, we look at the difference in electronegativity. If the difference is between 0 and 0.5, we say that it is a non-polar bond. If it's between 0.5 and 1.7, we call it polar covalent, so there would be a polarity difference. One is more electronegative than the other. And if it's higher than that, we call it an ionic bond. If it's 1.7 and up, that difference in electronegativity is going to tell us that we have a cation and an anion to give us that ionic bond. Electronegativity tells us how much a particular atom wants those electrons. As we just saw, electronegativity increases from left to right across the period, and it decreases when we go down. A molecule that has no polar bonds is a nonpolar molecule. A molecule with one polar bond is a polar molecule. If the individual bond dipoles do not cancel, then the molecule is polar. If they do cancel, it's nonpolar. If there are lone pairs in the central atom, the molecule is polar. Bonds that are polar are that way because not all atoms hold onto their valence electrons with that same force or take on additional electrons with equal ease. So electrons are not being shared equally between those nonmetals. We know this by looking at the electronegativity differences between two elements that are forming the bond. If the difference is equal to 0 or less than 0.5, we call it a nonpolar covalent bond. And actually, if it's, well, covalent can also be polar covalent, which is anything less than 1.7. If it's greater than 1.7, then it is an ionic bond. Going back to this table, again, we look at the differences in electronegativity. So if I wanted to look at HI, I would take H, which is 2.2, and subtract it from I, which is 2.7, and I would get 0.5, which is right on the edge, we can see, of being polar covalent and nonpolar. But we can also look at that and go, hey, those values, we can see that I is more electronegative. It has a higher value, 2.7 versus 2.2. So when we write out this molecule, we show that this end is slightly negative. That's the negative end of this molecule, and my hydrogen is the slightly positive side. Another notation is also to draw an arrow from or towards the more negative end of that molecule. So from the positive to the minus end. As that electronegativity difference increases, so does the ionic character of the bond. We can see that H2, when I took the H There we go up here. If I did H minus H, so 2.2 minus 2.2, we get 0. So that difference in electronegativity is 0. That gives us a totally covalent nonpolar bond. So as you can see, as we go left, we increase our covalent character. As I go right, so let's say I have HF. If I subtract, this is fluorine, and this is my hydrogen, so I subtract the two, I get 1.8. Now, I know that guide said anything greater than 1.7 was ionic. We know that H and F are both nonmetals, so it's got to be on the really high end of being a covalent, so we call it a polar covalent. And in this case, we definitely have a very much more negative end of the compound and a positive end of the compound. So it has poles, polar covalent. And then as I get even further more extreme, if I looked up lithium fluoride and took my F, my 4.0 minus Li, the 1.0, and I get 3, we can call this an ionic compound here, where I don't have any sharing of electrons anymore. We definitely have given and taken electrons to have a completely positive and a completely negative fluoride. Here's just reiterating, we said that a difference in electronegativity of 0 indicates that that bond is purely covalent. There is an equal sharing of those electrons. This difference is a little bit different from one text to another, and this is all from the same text, but here this is telling us that if we're between 0.1 and 0.3, that we are nonpolar covalent. 0.4 to 1.7 is polar covalent, and if we are, again, greater than that, we are ionic. Now, how do we know which compounds or molecules or whatever will mix together? Well, likes dissolve likes. So if I had oil and water, we know that they do not mix because water is polar, H2O. If I took H and O and subtracted them, I would get a polar molecule. And if I took my oil, which is a hydrocarbon, and subtracted those, it would be nonpolar. They don't mix. Ethanol and water do mix. I have a polar and a polar, so they would mix together. Here's an example of I2, molecular iodine. To find that difference in electronegativity, this one's pretty easy. I'm just doing I minus I to get 0. This is also sometimes called homonuclear. Notice that we have the same nuclei for iodine and iodine. Also notice the symmetry. If we cut it in half this way and in half up and down, that everything is mirror images of one another. This is also telling us that it's nonpolar because the bond is nonpolar. Looking again at HF, hydrofluoric acid, fluorine has the larger electronegativity value than hydrogen. We can look just by looking at this table, 4.0 versus 2.2. So when we are drawing out our Lewis structure or a 3D molecule, we can say that this larger number means that that is the more negative end, the more electronegative, because it has a higher electronegativity value. Electrons are shifting towards the flow. It's like playing tug of war, and fluorine is really winning. Let's look at the difference in electronegativity for 3 different compounds. If we compared HF versus CF versus OF, again, we're just going to subtract all of these values from one another. And then we can rank them. In terms of polarity, the greatest, the most polar would be the greatest number, 1.8, the most polar. So HF would be the greatest. The next one further down is CF, and then the next one even further down is that 0.5 would be OF. So all we're doing is looking at the difference in electronegativity. The greater it is, the more polar the bond is. So taking that information, which one of the groups is arranged correctly in order of increasing electronegativity? So why don't you pause and put these, take that chart, the electronegativity chart, and put them in order of increasing, with this furthest to the right is the greatest electronegativity. Hopefully you got this answer. Let's look at another. Which one of these is in order? So pause it. Hopefully you got this. Which one of these pairs would be expected to have the greatest bond polarity? So take a minute and pause. We should have gotten KF. Which one is the least polar of these? Hopefully you got CB. Here's another one. For each of the following bond pairs, decide which bond is more polar and indicate the negative and positive poles. So take a minute and pause. Okay, so I just took those pairs from A and B and wrote down their electronegativity values from the chart. So if we look at boron and fluorine at 2.0 and 4.0, the difference is 2. And boron and chlorine, 2.0 and 3.2, the difference was 1.2. So which bond is more polar? It would be BF in this case. And which one is more, indicate the negative and positive poles? So we would say that my fluorine is the slightly negative end, and my boron is a slightly positive end. Or we could also denote it and show the arrow to the negative end. Now, we could also say that this has the more negative end as well, chlorine, but it only asks us to do it for the one slightly positive end there. Silicon and oxygen, again, I just wrote down those values. I got a difference of 1.6, and P and P, I got a difference of 0. So silicon and oxygen also wins, and in this case, my negative end is the oxygen, positive end is the silicon, only because the oxygen had a greater electronegativity value, so it is the more negative end. It has a greater pull for electrons. Here's another couple to decide which one is more polar, and for each polar bond, indicate the positive and negative poles. We're going to look at HF and HI, BC and BF, C and SI, and C and S. So why don't you pause the video and complete those. Okay, so looking at the first two, letter A, HF has a greater electronegativity difference of 1.8 versus HI's electronegativity difference was only 0.5. And fluorine has the greater electronegativity, so my F would be my more negative end of the value of that polar molecule. When looking at BC and BF, BF has a greater electronegativity difference of 2.0. All we did was subtract boron from the fluorine. Boron is 2.0 and fluorine is 4.0, so a difference of 2, versus if I just did B and C, 2.0 and 2.5 is only a difference of 0.5. So the more polar molecule here is BF, with F being the more negative end of that molecule. And then last, CSI has a difference of 0.6 and CS has a difference of 0.1. So CSI is the greater. The C, if I look at C, it's 2.5 and SI is 1.9. So carbon end is my more electronegative end of the compound. SI would be my more slightly positive. This next section of our lesson is looking at charge distribution, combining formal charge and electronegativity. The way electrons are distributed in a molecule or an ion is called its charge distribution. Charge distribution can profoundly affect the properties of a molecule. Examples include physical properties such as melting and boiling points, and chemical properties like being susceptible to be attacked by an anion or a cation, or whether the molecule is an acid or a base. Now, the site of a charge in a molecule or an ion can often be learned from a formal charge calculations, which hopefully you're feeling pretty good about. But it is possible to get an incorrect result from this determination because formal charge calculations assume that there's equal sharing of electrons in all the bonds. Now, according to scientist Linus Pauling, there are two guidelines to use when describing charge distributions in molecules and ions. The first is the principle of electroneutrality. Electrons will be distributed in such a way that the charges on all atoms are as close to zero as possible. Okay, as close to zero as possible. And secondly, if a negative formal charge is present, it should reside on the most electronegative atoms. Similarly, positive charges are expected to be on the least electronegative atoms. So let's consider the concepts of electronegativity and formal charge together in these two resonance structures of CO2. A is our logical, probably logical first structure of CO2. But what is wrong with B? Because B still allows, everybody has an octet, but if we look at the difference between these two, first of all, we see that the formal charges on all of the atoms are zero, which is a favorable situation. In B, however, one oxygen atom has a formal charge of +1, and the other has a formal charge of -1. This is contrary to the principle of electroneutrality. Also, B places a positive charge on an oxygen atom, which is also unsatisfactory because carbon is less electronegative than oxygen. So any positive charge in this molecule should be on the carbon. Therefore, the best description for CO2 is structure A. At the same time, because the electronegativity of oxygen is greater than carbon, the polar bond is, so we can still show, we don't actually have to have that formal charge, we can still show in this bond that oxygen is slightly negative and that carbon is slightly positive, and we can show that just by doing our electronegativity subtraction and just showing that this molecule is polar. So let's use that same logic to decide which of the three possible resonance structures for OCN minus ion is the most reasonable. If we look at these, the formal charges for each atom are given above each element symbol. Again, we know how to find the formal charges. So looking at these three, which do you think is the most logical structure? Hopefully you were able to look at structure C and nix that one right off the bat. It's not expected to contribute significantly to the overall electronic structure because it has a -2 formal charge on the nitrogen atom and a +1 formal charge on the oxygen atom. So first of all, they're just larger charges. They're not close to neutral. And having that higher charge on nitrogen when oxygen is more electronegative and it has the positive value on oxygen, so it's just not going to happen. When we look at A versus B, A is more significant than structure B because the negative charge is placed on the most electronegative atom, oxygen. So this is the one that is probably most favorable. So we would predict that this one would be the more favorable structure. Also, if we have OCN and the O is the negative end, it's more likely to attract a hydrogen or a proton, and then that would create an acid. Back when we were discussing drawing Lewis structures, we said that the central atom is usually the atom of lowest electronegativity. So we would expect in this compound, CH2O, that carbon would be the central atom because it's less electronegative than the oxygen, so we would think it would look like this. Whoops. But here's an example or a case where we assigned the wrong atom as a central atom. So if we had the more electronegative oxygen as the central atom, notice that when we calculated the formal charge, we would find that the very electronegative oxygen atom has a charge of +2, and the carbon atom has a charge of -2. So not only does the more electronegative atom have a positive formal charge, but it's a large formal charge of +2. So that results from the requirement of having an octet around carbon and oxygen, again, because we got to have our octet for everybody to be happy. But this is just an example where, no, not favorable. We would want carbon to be that central atom, so we wouldn't have those formal charges. So why don't you take a second and try to draw the resonance structures for SCN. What are the formal charges on each atom in each of the resonance structures? And there's 3. Try to draw 3. What are the bond polarities, and do they agree with the formal charges? So draw that for SCN minus, and pause the video and we'll go over it in just a second. Hopefully you came up with these 3 different ways to draw SCN so that everybody can have their octet. And if we first started just looking at the formal charges for the middle structure is probably most favorable, although you could have also looked at this third one and been like, oh yeah, well there's a minus there and there's only one minus here, so the second and the third one charge-wise, we can nix right off the bat this first one because we've got a large formal charge. But if we look at the middle one compared to the right structure, the more negative formal charge is on the more electronegative ion. So we would want nitrogen, if we looked at our electronegativity sheet, nitrogen's electronegativity value is 3.0 and sulfur's is 2.6. So we would want to choose this middle structure since the negative formal charge is on the more electronegative atom. Then if we looked at bond polarity for our CN bond, if we subtract those 2.5 and 3.0, we get 0.5. So we can call this a polar bond, and my nitrogen is my more electronegative of the 2, so we can call carbon my slightly positive end. And if I looked at the sulfur carbon, we would have 2.6 and 2.5, so our difference would be 0.1, which is pretty nonpolar, but we could still say, since carbon has already been assigned as slightly positive for that middle, slightly positive, and we know that nitrogen is slightly negative, there might be just a teensy bit of a pull. Since that's positive, we can call sulfur my slightly negative end. It'll be a much less of a pull. Again, it's 0.1 with this bond than this one. This one is definitely going to be stronger. This next section is about molecular polarity. So our goal here is to be able to predict the polarity of molecules and understand why some molecules are polar where others are nonpolar. The term polar describes a bond in which one atom has a partial positive charge and the other a partial negative charge. Because most molecules have polar bonds, molecules as a whole can also be polar. In a polar molecule, electron density accumulates toward one side of the molecule, giving that side a partial negative charge and leaving the other side with an equal but positive partial charge. We've done this before where if I have HCl and I look at both of their electronegativities, subtract the 2, and I can see if there's a polar bond based on those differences, and then label my slightly negative end and slightly positive end of my molecule. Diatomic molecules like this that are composed of 2 atoms with different electronegativities are always at least somewhat polar because there's one bond and the molecule has one end that's more negative than the other end that's more positive. Unless they're the same, then that would be nonpolar. But if it's a diatomic like this, we always have one end that's slightly more negative than the other. But what happens with a molecule composed of 3 or more atoms? To predict if a molecule is polar, we need to consider how the atoms are positioned relative to one another and look at the polarity of the bonds as a secondary consideration. Here we're going to look at a linear triatomic molecule, so 3 atoms, we can see 1, 2, 3, like carbon dioxide, CO2. Here we have each carbon double bonded to an oxygen. Each one of those bonds is polar, this one and this one, with the oxygen atom at the negative end of the bond dipole. We can see the slightly negative end here and slightly negative end here. The terminal oxygen atoms are the same distance from the carbon atom. They both have the same slightly negative charge, and they're symmetrically arranged around the center carbon atom. So therefore, CO2 has no molecular dipole, even though each bond is polar. This is kind of like a tug of war where people at opposite ends of the rope are pulling with equal force. In contrast, water is a bent triatomic molecule. Because O has a larger electronegativity than hydrogen, we can see here that both of these bonds are also polar, but the electron density on the oxygen is much greater on this side. That's why it's made it bent. We have those lone pairs. So because it's electrically lopsided, it's polar. And we can see if we also notice the molecule symmetry, it can be broken along either OH bond axis. And we can, if we did this side does not look the same as that other side. So whenever there exists a line or a plane of asymmetry, the molecule is polar. Here's some more examples. If we looked at BF3, the B and the F bonds are quite polar because we know F is very electronegative compared to boron especially. Boron is a 2 and fluorine is a 4. The molecule itself though is nonpolar because the 3 F atoms around the edges, around the B atom, all have the same electronegative charge. They're the same distance from the boron atom, and they're arranged symmetrically around that central boron atom. And if you sliced this horizontally in half, because it's planar, the top half would look the same as the bottom half. So there is that symmetry to it. However, in contrast, if we looked at the trigonal planar molecule of Cl2CO, we can see the angles are all about 120 degrees. So there is symmetry arranged around the carbon atom. The electronegativities of the 3 types of atom in the molecule differ, however. We can see that this electronegativity is different from this one. This is a closer bond with that double bond. So therefore, a net displacement of electron density away from the center of the molecule, so more toward the oxygen atom than the chlorine atoms. So we can see by looking at this picture that there is a greater, red indicates a negative charge and blue is a positive charge. We can see that there is an asymmetry. We can see the symmetry around this one. They're all, each end is alike. This is not. And we also, if we looked at this one, NH3, ammonia, similar configuration is BF3, this is NH3, but remember that nitrogen has the lone pair electrons up here. So this is a trigonal pyramidal molecule, and the positive hydrogen atoms are located at the base of the pyramid right here. So the negative nitrogen atom is the apex of the pyramid. So therefore we know it's polar, right? Our slightly negative end is up here and slightly positive hydrogens, but we can see the non-symmetry because we have that electronegativity up here that's not matching around the edges. Looking at some more examples here, methane, CH4, and carbon tetrachloride, CCl4. Both of those are nonpolars because they're symmetrical tetrahedral structures, and the 4 atoms that are bonded to that middle carbon all are the same, have the same partial charge, and are the same distance from the carbon atom. But then if we look at these other 3 examples, they are also tetrahedral, but notice that we have our central atom and I have some different molecules around. Like here I've got 2 H's and 2 Cl's. These are polar because we can see the electronegativity for the hydrogen atoms is less than that for the chlorines. And because of this difference, the carbon-hydrogen distance is different from the carbon-chlorine distances. And because chlorine is more electronegative than hydrogen, the chlorine atoms are on the more negative side of the molecule. So the positive end of the molecule dipole is toward the hydrogen atom. So again, we wouldn't have that symmetry. And we can see that in this example and this example. So they're polar molecules if there is a net dipole. And we can see here in this case, this end of my molecule is positive and this end is negative. Here, no net dipole. Here we can see our negative end would be moving in this direction in between those 2 negatives. This would be my slightly positive end to the bottom left. We can see that this is my slightly positive end, so my slightly negative end has got to be moving over here to the right. Let's look at these 2 examples. Are sulfur tetrafluoride and nitrogen trifluoride polar or nonpolar? If they're polar, indicate the negative and positive sides of the molecule. Why don't you pause this here and draw these and see if you can take a guess. All right, first let's look at SF4. If we drew the Lewis structure, again, we would look at sulfur, have our 4 fluorines, we've got a lone pair for sulfur. So this would be a trigonal bipyramidal because of those lone pairs. It's pushing all of our F's over here, which is a seesaw shape. So we need to then decide if the molecule is symmetrical. It is not, so it's got to be polar. Let's look at NF3. And when we look at NF3 here, we've got our nitrogen with our 3 fluorines. So it's really similar structure to the NH3 that we were just looking at, because F right here is more electronegative than N. Each bond is polar. The more negative end being the fluorine atom. Because this molecule contains polar bonds, and because the geometry is not symmetrical, then we could say that NF3 molecule as a whole is expected to be polar. And we would say, oh, yep, this is negative. These are my negative terminals. This is my nitrogen, these are my fluorines. Negative, negative, negative. So as a whole, my net dipole negativity is going this way. My SF4, because of that seesaw, because I have my lone pair electrons right here on the left, my net dipole is going to the right. Here's another one. For each of the 5 molecules, decide whether the molecule is polar and which side is positive and which is negative. How about for BFCl2, NH2Cl, and SCl2? So why don't you pause the video here, draw these out, look at the differences in the bonds and electronegativity, and see what you can come up with. Let's see how you did. BFCl2 is polar. We know that the negative side of the fluorine atom is the most electronegative, looking at the bonds between BCl, BCl, and BF. So there's not that symmetry. And the FN is definitely the more electronegative. So the arrow will be pointing up. NH2Cl is also polar. And when we looked at those differences in electronegativity, the negative side of the chlorine atom is the most electronegative. And we know that the hydrogen end is the most slightly negative, or slightly positive, sorry. And so our electronegativity would be in this direction. And SCl2 is also polar. The chlorine atoms are on the negative side, so we can see that our arrows going down in between those chlorine atoms. Let's look at this example. We have 1,2-dichloroethylene, and it can exist in two different forms. Are either of these planar molecules polar? So take a minute and look at the two ways that this compound can exist and see if either are polar. Hopefully you were able to see that in structure A, the chlorine atoms are located on one side of the molecule. They're both down here. So electrons in the carbon-hydrogen bond and the carbon-chlorine bond are displaced toward the side of the molecule with the chlorine atoms. So the shift is down because of both of these chlorines down here. So it's away from the side with the hydrogen atoms. So molecule A is polar. If we look at molecule B, however, notice that the displacement of electron density toward the chlorine atom on the one end of the molecule over here is counterbalanced by the opposing displacement on the other end. So molecule B is nonpolar. So here's a picture of the electrostatic potential surface for SOCl2. Draw a Lewis dot diagram picture for this molecule and give the formal charge of each atom. Hopefully your dot diagram looks like this. We've got sulfur with a lone pair. 1, 2, 3, 4, 5. It's got 5 valence electrons, and it's also connected to oxygen and 2 chlorines. For formal charges, we've got sulfur with our +1, oxygen with -1, and chlorine with 0. And if you're not sure how to do those formal charges, be sure to go back and watch in the video as a refresher. Let's ask another question about this. What is its molecular geometry, and is it polar? What do you think? Well, if we look at the structure, and we know that sulfur has those lone pair electrons up here, it has to be trigonal pyramidal. The molecule's got to be polar. The positive charge is on the sulfur, the negative charge is on the oxygen. So we've got a polar molecule. Remember what we said about polarity. If those lone pairs are around the central atom, they will be considered polar. Here's a few examples for you to pause as you go to check your answers. Which one of these is polar? And hopefully you got CIF. Which one of these is polar? NCO3. Which of these is most likely to have a dipole moment? NF3 would. Which of these are polar? And lone pairs are not indicated on here, so you would need to think about that and look at those lone pair electrons. Hopefully you got B, C, and E. This last section that we're going to cover is about bond properties, looking at order, length, and dissociation enthalpy. So you should be able to understand the properties of covalent bonds, like the order, the length, and the bond dissociation enthalpy, and their influence on molecular structure and properties. So looking at bond order, the order of a bond is the number of bonding electron pairs shared by 2 atoms in a molecule. We will encounter bond orders of 1, 2, and 3, as well as fractional bond orders. When the bond order is 1, there's only a single covalent bond between a pair of atoms. Some examples are like H2 or NH3 or CH4. So here's an example of CH4. So there's only one bond between a carbon and a hydrogen here. The bond order is 2 when 2 electron pairs are shared between atoms, like in carbon dioxide when we have a double bond. The bond order is 3 when 2 atoms are connected by 3 bonds, like in N2. The bond strength increases with bond order. So a single bond is weaker than a double bond, which is weaker than the triple bond. So we've got bond orders of 1, 2, and 3. Fractional bond orders occur in molecules and ions that have resonance structures. For example, if we looked at this NO2 minus, notice that we have bond order of 2 between this NO and a bond order of 1 between this N and O. But it could also be, we could flip-flop that, and the 2 could be on this side and the 1 could be on that side. So therefore, we take that 3 total electron pairs used for a type of bond divided by total number of bonds of that type. So we would take 3 divided by 2 to get 3 halves, or 1.5, pretty much just averaging the 2 together. Another example is ozone, looking at O3. Each resonance structure of O3 has one single bonded OO bond and one double bonded OO bond. So for a total of 3 shared bonding pairs, accounting for 2 oxygen-oxygen bonds. So 3 divided by 2, this would also be 3 halves, or 1.5. When looking at bond length, it's inversely proportional to bond order. Bond length is the distance between the nuclei of 2 bonded atoms. It is clearly related to the sizes of atoms. Additionally, if we look at given pairs of atoms, the order of the bond plays a role. So if we look at sizes of atoms, like carbon-hydrogen bond, the length would be 110 picometers, is very small, so 110 picometers. But if we looked at silicon and hydrogen, so we can see the difference between carbon and silicon, and it's a longer distance, even though it's still a single bond, but we have a larger atom. So if we're looking at the center of the atom, if we're assuming that's where the nucleus is, it's going to be further to get to that hydrogen atom. Same if we looked at nitrogen and hydrogen versus phosphorus and hydrogen. Nitrogen versus phosphorus, phosphorus is bigger. Notice that that bond is longer. Oxygen, hydrogen, sulfur, and hydrogen. So oxygen, sulfur, sulfur is bigger. Notice that this is a bigger distance. If we look at the relationship between bond length and bond order, it's pretty evident when bonds between the same 2 atoms are compared. For example, if we looked at carbon single bonded to oxygen, double bonded, and triple bonded. So we have a bond order of 1, 2, and 3. Notice that my triple bond has the shortest bond length. And then second order is a little bit longer, and the longest bond length is with just single bonded atoms. And here's just another example of looking at the resonance structures of CO3 with a -2, so a carbonate ion, where I have a bond order of 2 with that carbon and oxygen, 1 and 1 between those carbon and oxygens. So that would be 2, 3, 4. So we would take that bond order of 4 divided by 3 different atoms, 3 different atom joinings. So 4/3 or 1.33, and our average bond length, it gives us is 129 picometers. This picture just kind of allowed us to see that distance between nuclei. If I looked at 2 of the same atoms, again, we're kind of measuring from nuclei to nuclei. We're able to measure that for 2 similar ones, and we can see that size makes a difference. If it's 2 carbon atoms, 154 picometers, versus 2 chlorine atoms, we can see that there's a larger distance there because they're larger atoms. And then we can also see if I just had C and Cl, how that is influenced. Here are just some pictures looking at HF, HCl, and HI. So again, we can see that we know as we go from fluorine, chlorine, and iodine that those atoms are getting larger, and we can see that that bond length is increasing with the size of those atoms. This also helps us to see visually if we look at the bond order. So here's a single bond, versus the double bond versus that triple bond. And we can see that triple bond is the shortest of all of these bonds. We can also see the bond order is proportional to the bond strength and bond length. So we've been talking about the length, but also the strength. Bond enthalpy is the energy required to break a bond in a mole of gaseous substances. So if I've just got a carbon-carbon bond, or a chlorine-chlorine bond, so a Cl2 is equal to 2 chlorines, we have an energy that we know this amount of energy is required to break that bond. And energy is delta H, enthalpy is positive, and if it's required to break a bond. And when those bonds are formed, energy is released, so our delta H is negative. So bond dissociation enthalpy is the enthalpy change when breaking a bond in a molecule with the reactants and products in the gas phase. The process of breaking bonds in a molecule is always endothermic. So delta H for breaking a bond is always positive. And if you think about it, to break a bond requires energy. To break anything, energy needs to be added to it. So that would be a positive value. Energy supplied, that means that H is greater than 0. And when you are breaking something, we're going from molecule, because there's a bond, breaking that bond, we then have the fragments. To go from the fragments to create a bond and make the molecule, energy is released, so delta H is less than 0 or negative. This slide we're going to need to be referring to quite a bit for when we're calculating enthalpies of breaking and forming bonds. So be sure to use this as a reference to switch back to. Here are just some examples where we can see this. So where we have bond orders being reflected in the bond dissociation enthalpies. To break the single carbon-carbon bond in ethane requires the least energy in this group. So we can see to break that single bond in ethane to then have just CH3 and CH3. So that bond between those is broken. We can see that it required 368 kilojoules per mole. And to compare that to breaking a double bond, we can see that it requires more energy. And compared to the triple bond, requires the most energy at 962 kilojoules per mole. And remembering that energy cannot be created or destroyed, the energy supplied to break carbon-carbon bonds must be the same as the energy released when the same bond forms. The formation of bonds from atoms or radicals in the gas phase is always exothermic. So if we look at the reverse of the ethane breaking of this bond, see how to break the bond, energy was required, so it's a positive energy. But to go back and do the reverse, where I take CH3 plus CH3 to form single bonded ethane, notice that it is a negative 368, so it is the opposite of this. Then we can calculate delta H by looking at the sum of whatever bonds were broken minus the sum of the bonds that were formed. Let's look at an example. So we know that bonds and reactants are broken if there's a reaction between molecules, and new bonds are formed as products form. So let's say I have this propene and I'm going to add H2 to get one product. So first thing we need to do is look at what bonds are broken, and I'm going to blow this up. So if we look at this, we can see that a double bond between a carbon-carbon is being broken. That takes energy. And you would not be expected to know this, but this is a known value that it takes 610 kilojoules to break a carbon-carbon double bond. We're also breaking an HH bond, which is 436 kilojoules. So it's a total of 1,046 kilojoules per mole required to break those bonds. Now we are also forming these bonds. So there's a certain amount of energy that's released when bonds are formed. And again, we would know that this carbon-carbon single bond, this much energy, 2 moles of CH. So that would be 2 times 413. This much is released. So then we do the bonds broken minus bonds formed to get a total of negative 126 kilojoules per mole. So we're also able to see that this reaction is exothermic because it is overall negative delta H. All of this data that we found for the energy is from a table that you would, it's average bond dissociation enthalpies, and those are all accessible for when you're finding these out. Here's just an example of what you would see. You would see an HH bond and you would be told that it's 436 kilojoules per mole, or a single bonded carbon to carbon is this much. So you just need to look, when you're looking at that table, just kind of scroll down to find what you need and to break a triple bonded nitrogen to nitrogen. Or if we were breaking it, that's a positive number. If we were forming that, then it's a negative number. Here's another example problem. Let's say we have acetone, common industrial solvent, can be converted to 2-propanol rubbing alcohol by hydrogenation. Calculate the enthalpy change for this reaction using bond enthalpies. So let's say we have acetone. Here's acetone structure plus H2. And here is our product. So can you see which bonds are being broken and which bonds are being formed? See if you can pause and figure that out. Hopefully you're able to look at that and go, wow, that definitely did not have a C double bonded O in the product. In our product here, there was a single bonded O. So we had to break that double bond. We also had to break this H bond because that was not in our product. There was H's attached. So we had 2 breakings. And if we looked at our data table, it requires this much energy to break the double bond and this much energy to break the HH bond. So that's our total for bonds broken. And if we look at bonds formed, we formed a CO bond, we formed an OH bond, and we formed a CH bond. So if we added up all of those, here's how much energy was released. So we did bonds broken minus bonds formed. And again, we can see we have an exothermic reaction with a difference of negative 53 kilojoules per mole. Here's the next one, using the bond dissociation enthalpies from the text, and I'll scroll to that in just a second so you can look at it. We're going to estimate the enthalpy of combustion of gaseous methane. So remember what a combustion reaction is. If I have methane, CH4, what does it need in order to combust? What is its other product? Or I'm sorry, what's its other reactant? CH4 plus what? To give water vapor and carbon dioxide gas. So think about what that reaction looks like. What bonds are breaking, what bonds are forming. I'm going to have you write this down. I'm going to scroll back to this table so you can get whatever data you need. So pause the video here. And now let's talk about it. We've got CH4 plus, hopefully you did oxygen plus O2 to give us CO2 and H2O. We had to balance the reaction. So what are we doing? We are breaking 4 carbon-hydrogen bonds, right? Because this is C with 4 H's around it. We're breaking 4 of those. And we're breaking 2 O2 bonds. Those are double bonded. So if we do all of that math, looking back at that table, we should get 2,648 kilojoules to break all of those. But we're going to make 2 CO2 double bonds, right? Because C is double bonded to O and double bonded to O. We're making 2 of those and 4 OH bonds. So if we total all that up, we should get 3,000. So if we do bonds broken minus formed, we should get negative 810 kilojoules per mole. And What is this? This is value calculated, oh, there we go. And it's very close to what it actually is, negative 802. So that is also telling us it's an exothermic reaction, which makes sense because if combustion, we're combusting something, that should be an exothermic reaction. So that wrapped up our last section in this unit or in this chapter. So we've got some problems for you to give a try to. So if you want to try to pause this and look and then I'll give the answer immediately following. And there you have it. Hopefully you were able to get those correct answers. And I will see you for the next chapter.